the test is positive, then we would say that this random variable x tilde is 1. And if it's negative, we would say it's 0. So we are going to describe these random variables in terms of probabilities, right? So if we observe this random variable many times, then the probability that x equals 1 is going to be the number of times that the test is positive out of the total number that we sample of x. So like we keep on repeating this sample, that's the total repetitions. And then there's going to be a probability that is approximately the number of times the test is positive versus probability that the test is negative, or x tilde equals 0. So if we want to say the variable p is the actual fraction of people in the city that have COVID, then we would say that this is going to end up being, again, p when we've actually sampled enough. We will know the value of p approximately. And then the number of times it's negative is just 1 minus p. So p is a fraction of 1, like less between 0 and 1. Sorry. It's like between 0 and 1, and like the probability it's negative is 1 minus p, so that the two probabilities will add up to 1. Either it's positive or it's negative. So how are we going to actually estimate it? Okay, we're just going to do a bunch of tests, and we're going to find the fraction of positives in it. So our test results are going to be some variables, x1 through xn, where n is the number of tests we're actually conducting. So our estimate of p is going to be the sum of x's, which means that it's the number of x tilde that are equal to 0, that are equal to 1, opposite, divided by the total number of samples n, right? So what could possibly go wrong? Okay, what if we just end up testing the same person over and over again? So it's still sort of an estimate of p. Each of these random variables has the same probability p of being 1, but we would end up with a value of either 1 or 0, depending on whether the one person who we just test over and over again has COVID. So the problem here is that these tests aren't independent. The same person might end up getting tested multiple times. So given that these tests are not actually like fully independent of each other, we need to start talking about the joint behavior of these random variables. That is, how do they behave in concert? So the joint probability, right? So we have these two random variables or more, but we're going to talk about what happens if we just have two. And we want to talk about what is the probability that they have a certain value at the same time. We are looking at x1 and x2 in the same world, the world we live in, and we want to ask, what is the probability that they end up actually having two particular values in concert? So if we just keep on regenerating them, then the probability over here, x1 equals 1, x2 equals 1, is going to be the number of times that both of these tests are positive out of the total repetitions. Okay. And then the probability that both are 0 is going to be the number of times that they're both negative out of total repetitions. So then the probability that one of them is 1, one of them is 0, that it's going to be the same regardless of which one is 1 and which one is 0, because we're generating them randomly. So like it's going to be, yeah. similar. Although, it depends on how you're sampling X1 and X2. Maybe these are actually different random variables in some settings. Okay, so that's the joint probability. So what is happening when we're looking at them together? So what happens if we were to fix X1 at a particular value? We say X1 is actually positive. Then what happens to the probability of X2? So let's think of this in another setting that isn't disease, right? So if you were to think of X1 as the probability of rain today, and X2 as the probability that the subway is shut down. So if there's like a huge amount of precipitation, and we know that X1 equals 1, then that's going to change the probability that the subway is shut down, because it's more likely to be shut down when there's a lot of precipitation. So if we want to generate them many times, then we would start to see this pattern emerge that the number of times that the conditional probability, which is represented by this bar notation, is going to show us that is going to approximately be, once we've sampled effectively, the number of times that they're both positive divided by the number of times that just the first test is positive. So in the example I'm describing, it's the number of times that there's precipitation and the subway is shut down divided by just the number of times that the precipitation is present, that there's snow or rain, right? So then we can say also that the number of times the subway is shut down, given that there is actually no precipitation, is equal to the number of times we see the probability that it's shut down, given that there's no precipitation, is equal to the number of times that the subway is shut down and there's no precipitation divided by the number of times that there's no precipitation. So this is a way of sort of partitioning out. The division is a way of partitioning out just the cases that align with what we know is true, which is precipitation or no precipitation, right? So if we want to think about it in terms of how these variables relate to each other, then we could say whether or not these are independent variables. So the case of precipitation and subway being shut down, that's clearly dependent. If there's precipitation, then it's more likely that the subway is going to be shut down. We've all probably, many of us have had this experience, right? Whereas if you were to ask about the probability that the subway is shut down, given that I wore my favorite shoes today, okay, that might be related to precipitation, but let's say that my favorite shoes are actually just my normal shoes that I just insist on wearing every day, actually, then it's not going to be affected by things like precipitation or whether the subway is shut down. Me putting on a particular pair of shoes today does not really influence whether the subway is going to be shut down, nor do they have like some shared factor, right? So so then you would say that these are independent variables. So you would say the probability that the subway is shut down is equal to the probability that the subway is shut down, given that I have put on my favorite pair of shoes that I wear every day, right? So now that we've talked a little bit about the conditional probabilities and joint probabilities and independence, we're just going to go back to this. Now we understand this idea of independence. So we know, okay, we're not just going to resample the same person over and over again. We want independent tests, right? So we're going to compute the number of positive examples out of a set of independent tests. So now we are summing up as before these variables x sub I, and we're getting this approximation y tilde, which is our estimate of the number of like real, cases of positivity. So this is also a random variable. xi tilde is a random variable. So is y tilde, the estimate of the number of positive tests. So the probability, yes?
Sorry to interrupt for a second. We have a couple of questions actually in the Q&A.
Oh, please, yes.
Yeah, so Rita, do you want to, actually, I can just read it, I guess. So dependent variables are given by an event influence, and independent variables is something that does not relate to an event.
So independent variables, sorry. Okay, so dependent variables. So dependence is a relation between two different variables. So you would describe the two variables as independent of each other. A variable is not like sitting around independent on its own. So the example that I chose, which is a terrible example because whether I wear shoes that I like that are like my favorite red boots or not is actually influenced by things like precipitation, which also affect the probability that the subway is shut down. But let's say I read my favorite book this morning. I love to read a book every morning, and whether I read my favorite book is not going to be related to whether the subway is shut down. Then there's independence between those two variables. It's about a relationship between them. A variable is not independent on its own. Every random variable is related to an event. It's just dependence and independence describes whether two random variables have some kind of shared influence. So this example actually of shoes is a pretty reasonable one, because if I wear my favorite red boots today, maybe it's because it's raining. And if it's raining, the subway is more likely to be shut down. So if you know that I wore my favorite red boots today, in that situation, you would be like, oh, wow, I bet the subway is shut down because they're wearing boots, right? But if I just wear my red boots every day and I do not care about what the weather is outside, then I'm like, oh, I'm wearing my favorite red boots today. And you're like, okay, well, I still don't know what the probability is that the subway is shut down beyond the normal probability. That gives me no information. So dependence and independence is really about the information that I'm giving you when I give you a particular variable and you want to know about another variable. That's the relationship between those variables. It's one of information. Okay. That's my explanation.
Awesome. Thank you so much. So I don't know if you can see some of the other questions here.
Let me see if I can. Let's see. Q&A. It's under Q&A, right? Okay.
Yes. Uh-huh.
All right. So it's on, is it under Q&A? Okay.
Yeah, so you should see this is open. We also have one hand raised too.
Sorry, open questions. I'm kind of just seeing a bunch of, okay, maybe like I'm not seeing
so there's a Q&A feature when you.
So for Retta, the idea, the example I'm giving of the shoes. Okay, so fixed variables. Okay, so there's an example about the fixed variables. When I say a variable is fixed, I mean that we know the value. So if I tell you whether I wore my red boots today, then that's a fixed variable. That means that you know the value. You're not sampling it. It's not like a random variable. It's, the randomness is sort of gone. So it's now fixed. Yeah, I told you I'm not wearing my red boots today. I'm wearing slippers because I'm not going outside. That might tell you about the precipitation level too, right? I don't know if that answers Sadman's question, but for Retta, so one way in which the shoes event might be related to the subway malfunction is if I have some kind of, there's like a conspiracy where the MTA is monitoring what shoes I'm putting on that day and then deciding whether to shut down the subway. So it might be related to some kind of superstition, but it might also just be that that there's a shared influence that the two things have. So when I put on my red boots, you're getting information about whether it's raining or snowing outside. And if you have that information, it also tells you something about whether the subway is likely to shut down due to snow and rain. So that there's multiple ways that you might get information about the subway shutdown from knowing about what boots I put on today. So, okay, Mustafa has a question regarding independent and dependent variables. Given that A and B are independent, can A and B change in the future and become dependent? So if you're looking at things over the course of time, that does introduce another factor, which is that your model can change of what you believe is happening, like what you believe is going on in the world. So if in this example, you build a model or you put together a set of assumptions about dependence and independence of your different variables that's based on the fact that I love my red boots so much that I will wear them every day no matter what, then you can say this is an independent variable. And if I get sick of my red boots and I'm like, I'm just going to wear these when it's snowing or raining, I'm not going to just keep on wearing them every day for the rest of my life, then you could say, okay, now this is a dependent variable. So they can become independent or dependent, but in order for that to happen, the model that you're thinking in of the world has to change. So you need to sort of think about whether your assumptions are correct and think about when your assumptions change. That's true. Okay, Davi Folletti has a hand raised. Do you want to ask a question?
No, sorry, my bad. I just hit the button. Sorry.
Okay.
Sorry.
That's fine. Anybody else with a raised hand, or shall I resume I'm just going to go ahead and resume.
Yeah,
All right.
I just want to make a quick note that like if you do want to speak up, then like via audio, we welcome that too. So raise your hand for that. And if you want to submit a text question, just use the Q&A.
All right. So we're going to talk about computing this probability that this random variable y tilde, number of positive tests, is equal to k, a particular number of positive tests. That's not a random variable. We're looking at if they match. Okay. So the problem we're going to run into when we want to compute this is that, first off, positive tests can occur in a bunch of different orderings. So we're going to need to, if we think about these joint probabilities, we need the joint probability of x1 equals 1, x2 equals 1, x3 equals 0, and as well as the probability of x1 equals 1, x2 equals 0, x3 equals 1, if we want to check whether this variable y tilde is equal to k. Is equal to k when k equals 2. So these are all of the different joint probabilities we would need to test. And when you start getting to the like 20,000 tests, obviously these are a lot of joint probabilities, and we're not just going to check every single possible combination of joint probabilities. These are all different orderings. So for whatever n again, the number of total tests, and K, which is again, the number of positive tests that we're checking against. We are looking at this, we're looking at the number of possible orderings, that is N choose K, which is N factorial over K factorial times N minus K factorial. Why is that? So first, let's remember that N factorial is the number of possible orderings, because it's the number of possible orderings of any N items, which in this case of the 20,000 tests would be like 20,000 times 19 times 19,999 times 19,998, et cetera, et cetera. And then if we want to pick out our K positive tests, 5 positive tests out of 20, let's say, then we're asking, okay, what's the first positive test we run into? We have 20 options. What's the second one? Now we have 19 options because we've removed one that we've declared to be positive, and we keep on multiplying, and we just multiply for each option that goes from 20 to 15, which is equal to N factorial over N minus K factorial, where N factorial is 20 and then N minus K factorial here is 15. But at this point, we've actually overcounted the number of selections, because we've just separately counted every possible ordering, because we've asked, what's the first test? What's the second test? We don't care. We just know what the total number of tests altogether that are positive is. So we only care what the total like selection of tests. We don't care what order we've picked them out in. So in order to sort of remove that overcounting, we then divide by the number of possible orderings that we've picked out, which is how we get this over here. So N factorial over N minus K factorial is again the number of possible orderings of positive tests that we could pick out, and then K factorial is how we divide by the orderings of the actual picked tests, to make sure that we're just talking about an unordered selection, because we don't care about the order. So
So if we have a hand raised.
oh yes, please. Whose hand? Go ahead.
Hi there, can you hear me?
Hello, yes, I can hear you.
Hi there, yeah, just a cool question. So with the previous joint probability mass function you were showing with, each like x1, x2, x3, etc., could we say that those are distributed as almost like a Bernoulli trial? And in the sense we can always either someone's positive or they're negative, so it's almost like one or the other. And then likewise, if we were to evaluate them on a more broader level, would it be like more representative of like a binomial distribution?
Yeah, that is correct.
Gotcha. And I know these are all these are all discrete random variables we're talking about, but like
yes,
I know that generally speaking that when we're working with like large distributions, like usually continuous can be more helpful. So if we were to let's say we had 20,000 participants, we wanted to sort of approximate that COVID distribution, would we in the sense like use central limit theorem and kind of have like summate all those random variables to almost use like the more Laplace's theorem?
Yeah, so the central limit theorem, thank you, is something that we can talk about a little bit at the end, just because it gives us guarantees that we sort of get more and more like Gaussian-y as we keep on sampling. So it's essential for a lot of guarantees that we use when modeling, because Gaussians are really nice to work with, right? For a number of reasons. I don't want to go super into it, but obviously there's like things like the fact that you can convolve a Gaussian with a Gaussian, you just get another Gaussian. There's just a lot of guarantees that are really nice with Gaussians. I don't want to get super into it because we're doing super fundamental probability questions right now, but yeah, thank you. We, I think, have other people's hands raised.
Yeah.
Or yeah, but yeah. Yeah, so Kishan?
Yeah, so I have a question. Does order doesn't matter in the probability of K positive test? Does order matter or does it matter? Like,
Does order matter?
Yeah.
So our goal is to make sure that order doesn't matter, because
Oh.
all we want is to make sure that we know the number of tests that have been that have been positive. So we
Okay.
don't want it to matter if the first person we tested and is positive or not. We just want to know that a person was tested positive. Yeah.
Okay.
So that's why we have to divide by k factorial to sort of partition out the like the orderings. So let's any other questions? All right. So once we have this, so we just talked about different orderings. Now let's say we have a particular ordering. Then what's the probability of K positive? It's the probability of the joint distribution of this fixed ordering showing up with that K positive, with like K positive examples of positive tests. So this gives us, if we have this independence guarantee, we can take this joint probability and turn it into just the product of all of the individual probabilities, because we can easily because we can remove the like conditioning aspect that we that they have if there's dependence between them. So this ends up just being p to the k, because there's k examples over here of 1, of like x equals 1, and then times 1 minus p, the probability that x equals 0, to the n minus k, which is the number of these examples that we look at. So if we look at every possible ordering, which we just talked about with n choose k, we can multiply that by the probability for arbitrary fixed ordering of having k positive examples. So when we are, when we're looking at this, then we might end up sampling something that looks like this. If you're looking at 100 tests, and let's say that 5% of those tests should be positive, right? Then we are looking at this curve that's kind of skewed. And that is where the central limit theorem is going to end up being relevant, but but this is like a little bit skewed. And actually there's like a really low probability, less than 50%, of actually ending up particularly close to that 5% over here, right? So that's really bad. And you only have 100 people you've sampled, which is a really tiny sample out of like 8-9 million people. So let's sample a little bit more. Oh, look at that. It starts to look like way less skewed, right? And the probability of actually ending up very close to 5% with, you know, with like an error, which is that like how far you are from this true average of 0.05 is going to end up really low, of 0.13, the probability. So then if you end up taking 10,000 tests, you get closer and closer to the true mean in your sampling. You're probably going to end up really close to the true mean at that point. So here you just end up just like closer and closer just as you sample more and more people. So here, So let's just like talk about what we just talked about. You need to understand how you got your data when you're modeling the variables. You want to model them as random variables. You want to think about the joint probabilities between those variables and the conditional probabilities if you want to actually think about the dependence between these variables. And also, if you can get independent random samples, then you will get a much better approximation of the actual statistics that you're sampling from. So just think about probability theory. It's super key to actually understanding machine learning. Because machine learning is all about learning from samples of data. And so that's, I think, the end of this segment of our chat. And I'll see you again at 11, I believe. Is this a correct statement to the organizers? Oh, Kishan, go on. There's a raised hand, yes.
Kishan, feel free to speak up.
Okay, so how does like machine learning apply to this concept?
Okay, so important, yes. So when you are training a model, all that a computer can really know is the data that you feed it. So when you feed it some particular random variable, when you feed it like a sample of data, all it can really learn is what you've presented it with, and you have to repeatedly present it with data. If you give it, for instance, if you give it really skewed data, similar to estimating the prevalence of a disease based on people who are choosing to get tested for it, if you are presenting skewed data, then the machine learning model is going to think that the overall statistics of what you're handing it are skewed from where they are. So for instance, if you, all of the examples I can think of are like really strong bias examples. So one example is if you are working with translation data, some languages will have gendered variables. Now I'm in this mindset. I mean, words. Some words are gendered. If you're speaking Spanish, your verbs maybe are going to be gendered, and so on. And if you're translating from English, then you might not encode that gender. And so the other language is going to have to pick up on it. And if your data, for instance, has a lot of male doctors in it, then when you hand over a sentence that's in English that says like, the doctor is administering vaccines, then when you translate the verb administering, wait, Spanish doesn't have gendered verbs. Some languages have gendered verbs, whatever. So the point is, you hand over this sentence, and the noun doctor might be translated as being masculine, when that's not necessarily the case in the original sentence. It might have said like, the doctor's administering vaccines and she's been working all night on it. And then as soon as you translate it, the sentence just becomes masculine because all of your data is so skewed towards a particular gender for doctor. So that's just like one example, but it happens like all the time. You just have a lot of problems in terms of how you sample data sometimes. This is an example based on like the data that's available to you, as opposed to problems with sampling itself. But there's also problems with sampling itself that you might run into. If you're dealing, for instance, with sampling some kind of structured information from an infinite distribution, and you're like actually generating the data itself, then you might actually, like, instead of, taking it out of a large body of sentences, you might end up generating something that's extremely unrepresentative. So that's one way that probability becomes extremely relevant. Yeah.
Thank you.
There's other ways also. You can build an entire machine learning model that's just about the relations between dependent variables, for instance. But like, yeah, basically it's everywhere is the answer.
Yeah. Thank you.
All right. Anyone else? Right. So we are coming back on at 11, right? Am I correct in understanding this?
No, sorry. I think my understanding is that we're trying to continue on with part 2 of the lecture now. If you want to do a 10-minute break, that's totally fine, but it's
No,
up to you. We can
that's
either. Okay. We've got plenty of other questions and hands raised right now too.
Okay, questions, go on. Oh, I see, Q&A. All right. Please share us some resources to understand better what we've discussed here. I can definitely post some of those, or the organizers can dig up their favorite basic probability tutorials. Are there other ways variables can be related besides independent? And I guess you mean dependent. Well, independence is just one way of thinking about how two different variables can be related. If we had far more time, I would show some slides that show little graphs with like nodes that connect to each other. So you might think, okay, one way you might think about things is causality. Causality is extremely relevant and extremely real in a lot of settings. And so, so one way to think about it is, I put on my red boots. Did they cause the subway to shut down? Or do we have a shared causal parent, which is whether it's raining outside? And I put on my red boots because it's raining outside, and the subway is shut down because it's raining outside. So this is just like one way that you can really think about the relationships between variables, is not just whether they're dependent, but what is causing one thing or another thing. But a lot of actual modeling of probability is not going to incorporate causality, because it's a lot easier to measure correlational information, although there are ways of turning correlations into causal relations. But you can't really, but if I say that a variable is independent of another, or is dependent on another variable, that doesn't mean that it is caused by that variable. Is Bayesian theory relevant for machine learning? Yes, extremely relevant. Some people are extremely Bayesian in the way that they think about things like sampling and like how you select variables in the actual like parameters of your models. Even if you're not a Bayesian, Bayes' rule is like everywhere. Because but this is going outside of sort of the scope of basic probability for many people. Yeah. So how do we differentiate between causation and correlation in data? That is very much outside the scope but I guess I have a sort of, let's say, a pop science book recommendation, which is The Book of Why by Judea Pearl, which is like fairly, targeted towards general audiences in explaining how you can think about causal effects in the world. I mean, one way you can differentiate causation and correlation is by actually intervening with a variable. So if you were to prevent me from putting on my red boots, then if you were to repeatedly like make me or like prevent me from putting on red boots, then you would get an idea of whether that is changing the subway shutdown schedule. And then you can make a claim about a claim about the causality of that. Engaging in in my opinion, engaging in Bayesianism would be beneficial for someone who wants to work with machine learning. So I would say that understanding Bayesian, Bayesian modeling, and when you talk about Bayesianism, it's really important to differentiate a certain type of like weird, sort of, I guess, philosophical stance from the like mathematical framework of Bayesianism. I'm not talking about like modeling the world around you with Bayes' rule. That's different from Bayesianism. I think it's important to understand the Bayesian framework, but it's also, I think, really valuable to understand the, like, say, alternative framework of frequentism. And I guess what I'm saying is that you should understand statistics. Many people are very Bayesian, and far more people are like secular Bayesians, are people who are more who like to look at things from a Bayesian perspective, but aren't committed to it in a strong way. I would say that it's important to understand if you want to get deep into machine learning. Yeah. Anyway. Any other questions, or shall we jump into the next segment?
I believe we have a couple of hands raised.
All right, so hands raised. So where are our hands raised?
Kishan, do you want to go ahead?
Yeah.
Okay, so I have a question. Is machine learning faster than AI in solving this problem, this problem?
These are really broad terms: machine learning, AI. AI is something that is so I would say that when people talk about AI, the main distinction is that people will often include some really classic, like not explicitly probabilistic methods under the AI umbrella. So I would say that when people are talking about AI, machine learning is usually a subset of that. And there is a tendency to favor statistical methods right now. So machine learning, I think, is currently, I mean, I'm saying it like we're ever going to go back to like just focusing really heavily on like on a star search or whatever. But no, that's not what I mean. There are certain non-probabilistic algorithms that end up getting incorporated into machine learning, but for the most part, everything is really statistical. There may be some points where different kinds of structure get incorporated, but I would say that machine learning as a subset AI is sort of dominant at this point. Yeah. Okay. Bhatia? Or, yeah.
Yeah, can you hear me?
Yeah. Yeah, go ahead.
Awesome. Yeah, so I do have a question. It is outside the scope of what we've covered, so you don't have to answer, but I was just kind of curious because I wanted to ask someone who's obviously done a lot of research and been in the industry.
Okay.
So like to my knowledge, like specifically for like moment generating functions, to my knowledge, I understand that if you essentially take the expectation of e to the t x, where x is a random variable that's distributed with some distribution, and differentiate it and out evaluate that at 0, you can essentially find the moment of any particular distribution. I'm assuming you know
Yeah.
of that, and obviously that can be pretty helpful in terms of evaluating. If you want to find covariances, or finding just the mean of it is the the
Yeah.
first moment, and kind of etc. like on with third, fourth moment
Mhm.
in terms of finding skewness or whatnot. So I guess to my question is, how prevalent are moment generating functions in machine learning? Have you seen, or like within the industry?
So I would say that so in statistics more broadly, people obviously use moment generating functions a lot more in modeling distributions. In statistics, I guess the methods or in machine learning, the methods that are closely related, though not exactly the same, that you might want to look at are things like understanding loss landscapes in terms of the Hessian matrix and things like that. So you can look at a loss function, which is when you're doing gradient descent. We're going to talk about gradient descent in the next half of the lecture briefly, but basically if you're looking at gradient descent, then you are taking then you can look at like the first and second and so on derivative of what's going on in order to get a more clear understanding of the immediate environment of the current settings of the parameters as they like move around the loss landscape, and to sort of understand better the like short-term movement of the parameters as you learn them versus the like longer term trajectory of those parameters. So that's the closest thing to talking about moment generating functions that people tend to talk about in machine learning in the areas that I'm in. I'm not going to make like a huge broad claim because there are people who are more traditional statisticians who are in machine learning, but yeah.
Gotcha. Thank you so much.
All right. Sorry. So now if you want to understand gradient descent, then just stick around for the second half of this because I will be pulling it right up. So now I'm going to so I am going to now pull up the next half of the lecture. Woohoo. I'm just going to take like a 2-minute break. Okay. I've set up the actual presentation. Can everyone see it?
Yep, looks good.
Great, perfect. All right, here we go. So, oh no, that's fine. We're just gonna understand regression and really, really basic linear algebra here. So we want to estimate a response from some number of features, P features. So this might be sort of pulling in an example from the first half. Maybe we have two features, and one of them is precipitation, and one of them is whether I've put on my boots today. And the combination of those two things is the information that you get about the subway. So you want to learn some function such that you are actually estimating this response from the inputs. Okay, first we're going to start with the linear regression because linear functions are very easy to talk about. So you want to estimate these coefficients beta from the training data that you're given. So an example that you might use for linear regression is trying to estimate GDP of a country from population and the unemployment rate in the country. So the larger the population, the larger the GDP probably is, but the larger the unemployment rate, the lower the GDP probably is. So you have Y, which is your GDP that you would want to estimate for a particular state. And then you have X1, the first feature, population, and then you have X2, the second feature, which is unemployment. So you would express this as a matrix, and you would express this sum of the features, population and unemployment, multiplied by some particular coefficient, which would probably be positive for population, but negative for unemployment rate. And then from that, you would get Y, which is GDP. So then you would describe Y train, which is the output that you would actually get from training. So or which is the Ys that you're actually feeding for training, right? So so one way to train a linear model is by using least squares. So the error is the distance from the actual Y, and so the energy of that error is going to just be the sum of squares. So the sum of squares being here, the distance between yi and the actual outputs of your model that you're training, which is the distance between y train and these outputs in a norm over here. So it's just going to be the sum of the squares of the distances. This is going to, so we're going to minimize this. So argmin is just the argument beta that minimizes this error function over here. So where we will be looking at this linear function, which is a literal actual line, which is the input x, the output y. You are just trying to find the slope of this line. In reality, you're going to also have like a sort of constant that you would add to it. But right now, we're just going to focus on learning a single parameter beta, which is the slope of this line. And you have data everywhere. You are trying to minimize that square of the distance from the line. So if you go outside of this area, you might actually need to model things in a nonlinear way, right? So one example of where you would probably want that is if you wanted to output a particular label instead of just a number that goes, along the line. You want to say, is this a sheep or a wolf that I'm looking at? So you want to compute the probability that what you're looking at is actually a sheep. And you have an input feature, which let's say is the change in the number of sheep that are in its pen. So maybe you're adding some sheep, but if this wolf is going around eating the other sheep, then the number of total sheep might end up going down, or at least go up by much less than it should be. So we're going to need to find a nonlinear function because this is clearly not a linear function. You've got your positive examples of sheep and your negative examples of wolf. You know that the probability that this is a sheep is 1 over here because you've checked these samples. And you know the probability that this is a sheep over here is 0. So how do you actually model this? You can't do it using a linear model. Like, this is just not a good fit. Instead, you need, you need something that looks more like this, which is logistic regression. So, everything over here is approximately probability 1 that it's a sheep. Everything that's over here, probability 0 that it's a sheep. And then everything that's over here is going to fall somewhere along this division. So how do you find parameters like this? Well, so you have this output that's according to the linear regression. And then you want to instead find a probability P that looks like this in the case of logistic regression. So in order to find it, it's actually quite difficult to just find this to look for an optimal solution to something that looks like this, where you're looking for beta. So we're just gonna multiply both sides by this. There's just a little bit of some simple algebra that happens, and then you end up with something that looks like this. At which point, if you take the log of both sides, you end up with an expression that isn't that different in terms of what you're going to be looking for, like how you're going to be looking for it, than the linear regression, because X beta looks pretty similar. So that means that you can follow a similar procedure for this, for any differentiable function, which is gradient descent. So basically, you might start out with some randomly picked beta. Doesn't matter what it is particularly. I mean, it does, but that's way outside of the scope of this. But let's say you pick some random value for beta, and then you take the derivative so that you can figure out which way is down. So you go down, 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 and then you get to a point where the derivative is 0 and you can't really go down anymore. And that's where you say, okay, I found my beta. So it looks like this in the actual math. You're just moving in the direction of the slope, where you're looking at this loss function, which, might be the like least squares energy function or whatever you're looking at. It's the thing you want to minimize. It's this little U-shaped curve, and you're looking for the perfect value. So while you're looking for it, you're just moving a little step at a time. So you have these step sizes that tell you, okay, I'm going a little bit down, going a little bit down. Really, you would want to get smaller and smaller in terms of your steps until you get to the bottom of this little basin. Okay, so that's how you actually find these values for any model you really want to look at. Now, going back to our linear model, you can estimate with this from least squares. You can say, okay, like we were saying, GDP proportional to the population, you subtract a little bit based on unemployment, and it looks like this. And going back to the linear algebra formulation, we are actually multiplying. We're actually taking each of these betas. Beta 1 is actually going to be multiplied by that first column. So beta 1 is basically multiplying by all of the features, all like by the first column, which is all one feature, but for all of the samples. Beta 2, you multiply by all of the samples with their second feature, and so on and so forth. Each of these corresponds to a particular feature in the input. In this case, you know, population, unemployment, population variable, and unemployment variable. So it ends up looking like this. If you say X1 is, you know, all of the population variables, X2 is all of the unemployment variables, and so on. Now we can run into a problem when we're training this. So if we choose a number of examples that is the same as the number of features, so in this case, it would be just 2 examples, and we end up with a square X, which is also invertible, which is not true of every matrix. But if we end up with an invertible matrix, we can actually solve this equation perfectly. We can get a perfect Y that is exactly the same as what we've trained with. Wow, that's so great, right? We've actually got 0 training error, except that it's actually not great, right? So we have these X inverse, not always available, but let's say it is in this case. X inverse multiplied by all of this little bit, which is the perfect beta that we've found, times X, the data, plus Z, some kind of the perfect beta that we should find, rather, times X, plus Z, which is some error that's introduced during sampling or in our model of the world. There might be variables that we don't have access to. So Z gives us some kind of noise. Okay, so now we can multiply everything here, and actually X inverse and X would cancel out. And we have our perfect coefficient and this kind of error that's introduced multiplied by X inverse. So that could end up being a really large factor, so that the beta that we've learned is nothing like this beta star that's the like true coefficients that we would like to find. So if we have this extremely like large error that's introduced, then we will be extremely confident in completely like memorized information. All we've learned really, like what we've really learned is how to model the noise really well. So we can't actually have this tiny number of examples. This goes back to earlier when we needed a large number of examples in order to effectively measure the correct mean or any other statistic, right? We also need to have a large number of examples relative to the number of features in order to get a good estimate of beta star, because otherwise we have just like a lot of noise over here that's going to mess us up. That's just going to be particular to these individual variables and shouldn't be factored into what we've learned. Okay. So yeah.
Oh yeah, so we have a hand raised.
Great.
Joanna, do you want to go ahead?
I wanted to ask about the slide that says minimize loss function L.
Uh-huh.
Um, oh, right, okay, so I copied that down wrong. Okay, never mind.
Oh, okay. All right. Any questions actually? Because this part was actually much shorter than I was expecting because we were okay. So a lot of models can be trained by gradient descent is part of what we're thinking about. A lot of machine learning is just gradient descent. Genuinely, so much of machine learning is just training things by this extremely generic method of just following the derivative. Yes, the gradient, same as derivative. If you're confused by it, gradient is basically the derivative, but looking at the whole matrix that you're learning, right? So overfitting is a real problem that you will run into if you don't have large enough sample sizes. And you should really like think about linear algebra when you're trying to understand these kinds of models. Okay, so does anyone have and also logistic regression, really important concept. If you're looking at neural networks, then these kinds of nonlinear functions that have this kind of like woo, kind of curve show up basically everywhere. All right. So are there any questions? I think that this was an extremely short part that I thought would take longer. So if you have any questions, feel free. Sumbo? Mm-hmm.
Hi.
Yeah. Hi.
Yeah. So I have a question regarding the logistic regression. So I'm just needing some clarity about the fact that the Bayes estimation, the one where we had the permutation of n minus k for like deterministic conditional variable, can we like model this using logistic regression, knowing like the sheep and the wolf scenario? Can I use the same conditional probability to model based on logistic regression, or this is only applicable to Bayes' theorem?
Okay, so when you're looking at logistic regression, the examples that you're given are going to be labeled, let's say 1 or 0, although you can work in a multivariable setting. Like rather multiple classes, but in the like binary setting that we're looking at, either sheep or wolf, definitely not a giraffe or whatever, you're given inputs that tell you, is this sheep or wolf, which means that you know that each example is either 0 or 1. You're not given like ambiguous examples that are labeled ambiguously generally when you're looking for a binary classifier like this one. So in this case of logistic regression, the logistic function, the bit that's not just, oh, this is basically 1, oh, this is basically 0, it mostly comes in this little in-betweeny bit, right? Which would give you probabilities between 1 and 0, right? Does that, I'm not sure if that answers your question. I'm not entirely clear. Do you want to rephrase your question if that didn't answer it?
Yes, I want to.
Sorry.
Yes. So what I'm saying is, if I have like a data column that says, okay, male is 1 and female is 0, and
Uh-huh.
I want to use a conditional probability that I don't know what fraction of my sample is female, but I know that
Uh-huh.
it's a sample from my data that is 1 or 0. And I say, okay, I have to use logistic regression because it's a binary classification anyway. I'm wondering, like, if I'm using conditional probability, do I think of it as a Bayes problem, or do I think of it as a logistic regression?
Okay, wait. So thank you for this question, because this is an important clarifying point I should make. These regressions are about labeling a new example. So before, when we were talking about random variables, we were basically talking about the example we were using was about the proportion of the population that has a particular property. These regressions are really about taking a single example, saying this is a new state. What is the GDP? This is a pen that contains some number of sheep, and here's like a, and here's the sheep that I want to figure out if it's actually a wolf. This is, today, is the subway going to get shut down this one particular day? So you're looking at a single example and you are trying to label it as, yes, the subway will be shut down. No, the subway will not be shut down. And, the variable you have is, let's say, the amount of rain that happened today, right? That's the input that you might be modeling from, right? And it's like, oh, it's like there's 10 inches of rainwater or whatever. Okay, well, now the subway is almost certainly shut down. And if they're like, oh, it's like tiny drizzle or whatever, then you can say, okay, subway's probably not shut down. So you're just making this single classification decision, rather than asking what proportion of days is the subway shut down this year. Does that make sense?
Yeah, I understand. So we have no past information. It's just basically what we have now. I understand. Thank you.
Okay. So let's see. Someone, okay, Tamirian asked, is logistic regression better for analyzing heart disease data sets, or should we use decision trees? This is one of these things where, there's people hate that decision trees are so good because they're not that interesting. So, okay, I'm gonna also, Khosrow asked to see the slide after the logistic regression graph. So I'm just putting that up. But now, okay, logistic regression can be a really good way of doing any kind of classification problem. The question might be, what type of input are you using? So if your heart disease data set has a lot of inputs that are themselves, let's say, binary classifications, like let's say that men are more likely to get heart disease or something, then that's something that decision trees would be really good at handling. When it comes to a bunch of inputs that are numerical, then sometimes decision trees are really, really good at handling that, but not always. That's the kind of question that you have to just like pull up your little, R or whatever, and just see what happens. Because both can be very effective ways of modeling. Nobody likes the fact that decision trees are so good because they're not like cool systems that you can, do weird stuff with. They're sort of like really, it's a tree, but they can be really good. Yeah. Ashish asks, how can we practically implement these mathematical equations? Genuinely, you can, when you are dealing with a differentiable function, you can actually just throw it, like, throw the derivative into your gradient descent function. But the way that we usually do it is by using an automatic differentiation library. PyTorch is an example of this. It shows up also in, TensorFlow. There's like a lot of automatic differentiation libraries. And you would just hand them the function, like you would show them, okay, I want the, I want to learn this function log p over 1 minus p, blah, blah, blah. Like you want to learn, this variable that isn't set. And then the automatic differentiator would just do it for you. That's generally how people do it. Let's see, Tamirian. Oh wait, first I'm gonna go down. All right, Ashish, how can we use logistic regression in a convnet? And can we use it in human mobility tracking system? These are like pretty specific to your model that you're going to end up using. You can, so the reason why logistic regression is really important, and we're going over it, is because these kinds of nonlinear functions applied to the application of this kind of nonlinear function is so essential in neural networks. The shape that you see, this little sigmoidal kind of shape, is one that shows up all over the place in neural networks, but you can choose different nonlinear functions. This is not the only nonlinear function that you might use on the output for a neural network. So a convolutional neural network could use many different kinds of nonlinearities at the actual output. But yeah, it's not wrong to think of like many types of classical neural networks as basically being logistic regression, but with more matrices that you're learning parameters for. There's yeah. There's some Boolean. Okay, so let's see. Yeah, so Tamirian, yeah, I think that you could, that's a perfectly valid system to throw at a decision tree or a decision tree forest, and compare that to what happens with logistic regression or many other models. There are many models that you can use and compare. You might even do things like split up the model according to some of the Boolean values. Like with heart disease, there's a tendency for like male and female expressions of heart disease tend to be quite different. So you might even end up wanting to just build two separate models for something like that, since the expression of that particular disease is so different in those two groups. Yeah. So any other questions? Am I missing raised hands or anything like that? I'll give you one more minute to raise your hands or enter new questions into the chat. And then we can wrap up and everyone can relax before their like demo lab. Yeah. The Q&A sessions, yes. Wait, have I missed Q&A? Oh, yeah, okay, sure. Great. All right. What made me research in the field that I'm in, which is Okay, so let's see. This is a long personal history, but I'll be brief about it. When I was a teenager, I was really into programming, but I was really into like security system stuff, that kind of thing. And when I was 16, I attended a lecture by a researcher who was working on that was like targeted towards teenagers. So it was a lecture about a method called collaborative filtering and creating common sense for machine learning models. And I sort of, at the same time, I was reading some really interesting books, Gödel, Escher, Bach, and Snow Crash, that both made me think a lot about language and AI, and it made me really want to do research in the area. So when I started undergrad, I found, so I sent an email to every single professor who was doing research in a related area, asking if I could work with them when I was like a freshman. And I ended up having some really great opportunities to do research from that. And then I sort of shifted, as many people do, from these really concrete problems of like, how do we do common sense? Like, how do we think about language, to really abstract problems about how does structure get learned by these extremely generic models that are all just trained with this, like, you know, gradient descent method. How, like, we're not telling them what to learn. They're doing it on their own almost. So how does that actually happen? Are they building it up piece by piece? So that's the short answer. Everybody who does any kind of research has like a long list of like 15 little steps that brought them to where they are. How to start individual research in computer vision as a second-year undergrad. I was extremely lucky and very privileged in this. But if you, but I would recommend looking for professors who are doing stuff that you're interested in. And I would recommend looking up REUs, Research Experience for Undergraduates, which are specifically targeted towards undergraduates who want to start doing research, as the name would imply. Okay, when it comes to image recognition, what are some, REU? Look it up, definitely look it up. Right. Someone else loves Gödel, Escher, Bach. Okay. When it comes to image recognition, what are some of the struggles when working with complex still images? One of the struggles is that the model will often end up focusing on something other than the thing you want it to label. So the classic example of this that everyone loves to use is if you show a cow on a beach to a model, it'll be like, I don't know what that is. That's probably just like, I don't know, a whale, who knows? Like, because it's been looking at the grass behind the cow in every example you've been handing it. So, so that's one example of where the struggles are, is you don't, is that because you have a particular bias in the data set, you're going to end up with a model that learns things that you didn't intend for it to learn. Yeah. We've got one more minute. Yeah. So yeah, I'll take the last minute to give the missing gap in my research history, which is that I was really interested in like social media data and language in that sort of respect. And that got me interested in how you deal with shifting from like standard domains to these like weird domains that are more informal social media data, like social media language. And being interested in how domains shift got me really interested in something called curriculum learning, which is looking at what happens when you introduce data in very deliberate ways, like simple data and then more complicated data gradually. And that got me interested in training dynamics in general, understanding the training process. And so, yeah, that's the missing gap in my research story. Everyone has the like 15 steps that got them to where they are. So, yes. I definitely recommend reaching out to professors in your institution who might be interested in supervising you on a project. It might or might not work. I emailed like 15 people when I was in my freshman year, and one person got back to me.
Yeah, and I wanted to put in a plug here. We're going to have a panel later today on building a career in AI or ML. So that also would be perfect for these questions. All right, so it looks like we're at about time. And Naomi, thank you so much. That was such an informative talk, and I loved listening to your answers to all the questions too. And thank you everyone for attending. We have office hours starting soon, so we'll see you all there. Thanks everyone.
All right, thank you
Bye.
for showing up. Bye.